In a formal system architecture, observational dependence and causal dependence are structurally distinct properties of the system model. Two system variables are observationally correlated if they co-vary under the probability measure. Their joint distribution carries information about each other. Two system variables are causally related if an intervention on one variable changes the distribution of the other. These two properties do not imply one another. A system architecture that conflates correlation with causation will design interventions on variables that are observationally associated but causally irrelevant, producing control actions with no effect. Conditional probability is an operation defined on the probability space. The conditional distribution of y given x equals x is the distribution of y restricted to the subensemble where x takes the value x. This operation does not alter the causal structure of the system. It selects a subset of trajectories, but does not change any transition law. Conditioning is an observational operation. It answers the question, given that we observe x to be x, what is the distribution of y? It does not answer the question, if we set x to x by intervention, what would happen to y? The do operator formalizes intervention in a causal system model. The expression p of y given do of x equals x denotes the distribution of y when x is externally set to x by an intervention that removes x from its natural causes. This is structurally distinct from the conditional distribution p of y given x equals x, which is computed without any external manipulation. In a system where x is caused by a common upstream factor that also influences y, the two quantities diverge. Conditioning on x absorbs the confounding effect. Intervening on x removes it. The do operator captures what changes when the system is modified, not merely when it is observed. Confounding arises when a latent variable influences both an upstream and a downstream component, creating spurious observational dependence between them. In a graphical system model, confounding corresponds to a common cause node with edges into two or more downstream variables. Observational dependence between the downstream variables is real. It is present in the data and in the joint distribution, but it does not represent a direct causal link between the downstream variables. An intervention on one downstream variable will not change the other downstream variable because there is no causal edge between them. The observational association exists only because both are caused by the shared upstream factor. Selection effects produce observational dependence that does not reflect a causal link between the selected variables. When the set of observed system states is determined by a selection criterion, the observed joint distribution is conditioned on the selection event. Variables that are independent in the full population may appear associated in the selected subpopulation. This is a consequence of conditioning, not of any causal relationship. System architects must account for selection mechanisms when using observational data to infer causal structure. Otherwise, spurious associations will be misidentified as causal dependencies and produce incorrect control designs. Simpson's paradox is the canonical demonstration that aggregate observational data can reverse the apparent direction of a causal effect. An association observed in a combined dataset may be reversed in each subgroup when data are partitioned by a confounding variable. This reversal does not require any error in the data. It is a structural consequence of marginalizing over a variable that is causally relevant. For system architecture, the implication is that aggregated performance metrics can point in the wrong direction when a causal variable has been averaged out. Correct causal inference requires specifying the causal structure of the system model before interpreting any observational statistic.